We were discussing about decomposition. So I told you what is a natural join and what is a Cartesian product. So here we are going to discuss about what is a lossless join. What is a lossless join? Okay, or you can say lossless join decomposition. What is a lossless join decomposition? Lossless join decomposition. Okay, assuming that we have a relation R, so we want to break this relation R into two relations, assuming R1 and R2, such that if we join these two relations, then we should get the same relation R. Then the decomposition is called as lossless. Okay, so you can define it like this: let R be a relation, let R be a relation scheme, and F be a set of functional dependencies, and F be a set of functional dependencies over R, and the decomposition of R into R1 and R2 is said to be lossless decomposition, is said to be lossless decomposition with respect to F, if and only if R1 natural join with R2 is equal to R, right, and where this is representing the natural join. Okay, now let us take this example. Assuming that we have this relation R, which is having the attributes A, B and C, and these are the values of these attributes. They are A1, B1, C1, A2, B1, C1, A1, B2 and C2. These are the attributes, or these are the values which are stored in this relation R. Now there are different ways of breaking this relation. What are the ways you can break? See, the first way, you can take one attribute in one table. That means you can make a table for A and you can make a table for B and C. Okay, this is how you can break, right? Or you can make a table for AB. This is representing the table for AB, A and B, and you can make one table for C. Okay, the second way of decomposing, or you can take A and C in one table. This is representing A and C, and you can take B in one table. You can take B in one table. Okay, this is the first way of decomposition. Now, or you can take some attributes as common, like for example, we can take A and B in one table and B and C in another table, B and C in another table, or you can take A and C in one table, A and C in one table, and B and C in another table, B and C, or you can take A and B in one table and A and C in another table. Okay, so that is A and C. So these are 6 ways of decomposing this, right? So there are more ways possible, but these 6 ways are suitable for our purposes. Now we want to decompose in such a way that if you join these two tables, for example, if this is a relation R, this is a relation S, if you join the relation R join S, then you should get the original relation, which is this one. Okay, so or maybe make it P or S, that will be better. So assuming this is the relation P and this is the relation S, so if you do P join S, then we should get the original relation, which is R. We should get the original relation, which is R, and we should not get any extra tuples, and we should not get any less tuples as compared to the previous relation. Now if that happens, then the relation is called as lossless, or then the join is called as lossless. Okay, or you can say decomposition is called as lossless. Okay, I'm confused always when I speak something. Okay, so anyways, so this is the relation P and this is the relation S. Now here in attribute A, the values can be A1 and A2. Here I'm taking these values from here. In this tuple B, in attribute P, we can have the value B1, C1 and B2, C2. In the same way here, if this is P and this is S, this is P, this is S, this is P, this is S, this is P, S, P and S. So here if you take the values of A and B, it is A1, B1, A2, B1 and A1, B2. For C it will be C1 and C2. In this table it will be A1 and C1, A2, C1, A1, C2, and this is third table S, which is B1 and B2. Okay, in the same way here you can have A1, B1, A2, B1, A1, B2. In B and C you will be having B1, C1, B2 and C2, and here in this case it is AC, so it is A1, C1, we can have A2, C1 and A1, C2. In this case we'll be having B1 and C1 and B2 and C2. Here A1 and B1 and A2 and B1 and A1 and B2. Here we'll be having A1 and C1, A2 and C1, A1 and C2. So these are 6 ways of decomposing these tables. Okay, now we know that if we do a natural join of two tables, like if we do P in natural join with S, and if we take the attributes of P and the attributes of S, if there's no attribute which is common, then natural join will act as a cross product. Okay, you can say if we say that P is containing the attribute A intersection S is containing the attribute B and C, because there is no attribute which is common, that is why this natural join will act as a cross product. Okay, now if you do cross product of two tables, the first table is having n tuples and the second table is having m tuples, then you will be having n cross m tuples in the resulting table. Okay, now you can see in the first table what is happening. Here this table is containing two tuples, this table is containing two tuples, and you can see in both the tables there is no attribute which is common, right? So if we do P in natural join with S, therefore we are going to get at least 4 tuples. Why 4 tuples? Because if there is nothing in common, so this natural join will act as a cross product. So we are going to get 4 tuples, but the original relation is only containing 3 tuples. Hence this decomposition is not lossless, it is lossy, right? Because we are getting some extra tuples, maybe we will be missing some original tuples, right? You can take the combinations like this. If we this natural join of P natural join with S, so we are going to get the attributes A, B and C. In these attributes we will be having the values as follows: A1, B1, C1, A1, B2, C2, A2, B1, C1, A2, B2 and C2. Here you can see this is already present in the original table. This is not this is present in the original table, this is present in the original table, but this tuple is not present in the original table. That means we are getting some extra values which is not present. Okay, so getting some extra values is also wrong values. Okay, so this kind of decomposition is lossless. Now here again you can see if there is no tuples in common, so there is no attributes in common. So if we do P natural join with S, it is containing 3 tuples, it is containing 2 tuples, so this P natural join will act as a cross product and we are going to get 6 tuples, but the original relation is only containing 3 tuples, so this decomposition will also be lossy. Okay, here again there are 3 tuples, here there are 2 tuples, so natural join will act as a cross product, so we are going to get 6 tuples. Okay, so obviously all these 3 decompositions are lossy. Okay, now if you check the second row, here you can see the first they are having one tuple in common, that is one attribute in common, that is B. So if you do P natural join with S, in this case of P natural join with S, we are going to get the attributes which is A, B and C. Because B is a common attribute, so we are going to combine the tuples according to P. So we are going to get the values which are A1 B1, A1 B1 C1. Why? Because this B1 and this B1 is common. Here it will not be combined because B1 is not equal to B2. Next we are going to get A2 B1 C1. Next we are going to get A2 A1 B2 C2. A1 B2, that is A1 B1 C1, A2 B1 C1, A1 B2 C2. Okay, so if you check, compare with the original value, so here we this is present in the original value, this is present in the original value, this is present in the original value. Therefore this decomposition is lossless because we are getting the actual table which is already there, that is relation R. If you combine this table, let us check what is happening here. So if you combine this table, that means if you do P natural join with S in this table, then we are going to get a table which is having the attributes as A, B and C. So we are going to combine those tuples only where the value of C is common. So here we have C1, here we have C1. So we are going to get the attributes as A1, B1, C1. Here it is C2, so it will not be combined. Next is A2, B2, so A2 B1 C1, because this is equal to this, and the third one is A1 B2 and C2. So these tuples will be combined. You can see what are the values which are common. This is already there in the original data, this is there and this is there. So this is also a lossless decomposition. This is also a lossless decomposition. Further, if you check this one, the last one, if you take P natural join with S, then can I get the original relation which is R? Okay, so here again the common tuple is, common attribute is A, so we are going to get the new relation which is ABC. Now let us see what are the values we can get. So the first value is A1 and here also A1, so A1 and A1 will be combined, so we are going to get A1 B1 C1. Here it is also A1, so we are going to get A1 B1 C2. Here this is also A1, so we are going to get A1 B2 C1. This is also A1, so it is A1 B2 and C2, and this is A2, so we are going to get A2 B1 and C1. So you can see we are going to get only 5 tuples here, and because this we are getting some extra tuples, therefore this decomposition is lossy. Okay, now if you check all the 6 examples which I have taken, in all the 6 examples here, in these cases we are always getting a lossy decomposition. But our aim is to decompose the table into a relation into 2 tables in such a way that if you combine these 2 tables, then you should get the original table. Okay, you should get the original table. So if you do this one, like this is, in this case you can see this is the relation P and this is the relation S. Okay, so here why we got the lossless decomposition, here we need to identify why we got the lossless decomposition, but here we are getting a lossy decomposition. So in 2 cases, in 4 and 5 we are getting lossless decomposition, but in case number 6 we are getting a lossy decomposition, and we do not want lossy decomposition, right? So what is the reason why we are getting lossless decomposition? If you do some research on this, if you try to analyze these values, then you can clearly see what is the reason why we are getting this kind of lossless decomposition. The reason is that there is an attribute which is common in those tables. Like here also there's one attribute which is common, but there's an attribute which is common in these 2 tables. And the second thing is the attribute which is common is a key attribute is in at least one of the tables. So you can say the common attribute is the key attribute in at least one of the table. So common attribute is a key attribute in at least one of the table, right? So for example, here in 4 and 5 we have common attribute as B, but is it a key attribute in one of the table? Key attribute means this B should be able to determine C, or this B should be able to determine A. So that means in at least one of the table, the B should determine all the other attributes. Okay, now you can see what are the functional dependencies which are there for this original table. Here, can I say A determines B? Can I say A determines B? No, I cannot say. Why? Because A1 and A1 is there, and it is matching with two values. Can I say B determines A? No. Why? Because B1 and B1 is compared with two values. Can I say A determines C? No, I cannot say. Why? Because A1 and A1 is matching with the value C1 and C2. Can I say C determines A? No. Can I say B determines C? Yes. Can I say C determines B? Yes. Right, you can check with this table. We have already done the functional dependencies before. So here in this complete table, you can see B determines C and C determines B. This functional dependency is valid. So here you can see the common attribute is B and B determines C. Therefore, in this table, B is the key attribute. B is the key attribute, right? In the same way, here you can say C is a common attribute. Here, C is the key attribute in this table. So if the common attribute is at least a key attribute in at least one of the table, then the decomposition is called as lossless. Otherwise, the decomposition is lossy. So this is the crux of this. Okay, so let me write it down in the next slide. So I am saying that the decomposition of R, the decomposition of R into two relations, which is R1 and R2, is said to be lossless if the attributes that is common in R1 and R2 is a key in either of the relation, right? Or you can say or one of the relation, then it is a lossless decomposition. So you can define it like this further. Let R be a relation, and F be a set of functional dependencies on R. Now the decomposition of R into R1 and R2 is lossless if and only if the F plus, that means a closure set of this functional dependency, contains either the functional dependency, which is R1 intersection R2 determines R1 minus R2, or R1 intersection R2 determines R1 minus R2. So in the first case we have R2 minus R1. Here we have R2 minus R1. In the second case we have R1 minus R2. Okay. So let me give you an example of this. What I mean to say from the above statements. You can say consider a relation R A, B, C with functional dependencies, that is A determines B. Now is decomposed into the relation R1AB and the relation R2BC. Now we need to check whether the decomposition is lossy or not. Check whether the decomposition is lossy or lossless. Okay, so what is the solution to this? So if you have R1 and R2 are the two relation, R1 is having AB and R2 is having BC. So if you take R1 intersection R2 determines R1 minus R2, okay, or we can say if R1 intersection R2 determines R2 minus R1, then the decomposition is lossless. Okay, so you can see in the first case we are saying R1 intersection R2. So R1 is containing the attribute A and B, and R2 is containing the attribute B and C. So what is R1 intersection R2? R1 intersection R2 gives us B, that is B is a common attribute. And what is R1 minus R2? R1 minus R2 is giving us no, if you do a comma b, this is a set representing a comma b minus b comma c, then we are going to subtract the values which is a common. So you can say a comma b minus b comma c is going to give us the value which is a. So r1 minus r2 is a. So the first statement, this statement is saying, this complete statement is saying r1 intersection r2 implies r1 minus r2, or you can say r1 intersection r2 determines r1 minus r2. That means b determines a. Is it there? Can we say b determines a? No, we cannot say, because this is the functional dependency which is not given. In the second case, you can see what is r1 intersection r2, that we already know. R1 intersection r2 is b, and what is r2 minus r1? R2 minus r1 is b comma c minus a comma b. So if you do that, then you are going to get c. So you can get c. So this means that b determines c. So is b determines c is a functional dependency here? If it is a functional dependency, then the decomposition is lossless. Okay, but you can see from this above functional dependencies, this b determines c cannot be inferred from this. Therefore, this does not exist. Hence, the decomposition is lossless. That means if at least from the table the common attribute is not a key attribute, because in both the tables the common attribute is b. So here either b should determine a or b should determine c. If any one of these happens, then the decomposition becomes lossless. But because none of these statements is happening, therefore the decomposition is lossy. So this decomposition is lossy. Okay, so you can write it down. You can take the next example here. Assuming that we have the relation r a comma b comma c, and this is the functional dependency which is given, that is a determines b. Now the relation is decomposed into r1 ab and r2 ac. So we have to find whether the decomposition is lossless or not. So what you can do, you can take r1 intersection r2 determines r1 minus r2, or r1 intersection r2 determines r2 minus r1. So what is r1 intersection r2? That means what is the attribute which is common in both of them? That is a. And what is r1 minus r2? R1 minus r2 is going to give us a comma b minus a comma c. So that is going to give us b only, right? So is a determines b, that means there should be functional dependency which is a determines b. And second case is saying this is a and this is c, either there should be a determines c. So you can see here a determines b is already given, so therefore this decomposition is lossless. Or in other words, you can say that the common attribute which is a here is key attribute in at least one of the table. That is why the decomposition is lossless. Okay, so now let us take a few more examples in the next video.